This is the second example applying maxima or minima. It is a digit problem. You are watching differential calculus. Two numbers have a sum of a if the product of one with the cube of another is maximized. Having two numbers involved, we can notate x and y. From the first part of the premise, adding x and y will result to a. So from this equation, we can also say that y is a minus x. The remaining part of the premise states that the first equation is valid if the product of the numbers with 1 being cubed is maximized. The function includes the product p, which is equal to x cubed times y. You can also treat the cube for y if desired. Taking the first setup, p then becomes x cubed with the substituted y of a minus x. So the product p becomes ax cubed minus x raised to 4 after distributing the monomial. As stated in the premise, the product should be maximized. Thus, we differentiate the function. dp over dx then is equal to a times the derivative of x cubed, which is 3x squared. Chain rule also requires d over dx of the term x. The second term is differentiated as 4x cubed with d over dx from chain rule. dp over dx is maximized, so it is zeroed out. dx over dx on the right is also taken as 1. So the function is simplified as 3ax squared less 4x cubed as equal to 0. We can solve a cubic equation or extract some factorable terms. Let's take out x squared from both terms, making x squared times the binomial 3a minus 4x. So by zero property, we can say that x squared is 0, or that is x as 0. This isn't feasible because if we multiply 0 with y, the answer will end up as 0, not a, which contradicts the first equation. Take the binomial and equate it to 0. That is 3a minus 4x is 0. Transpose one term and have 4x as equated to 3a, where x is then 3/4 of a. This is a feasible result. So back to the first equation, y is a minus x, or that is a minus 3/4 of a, leaving y as a quarter of a.